This video is about mathematical induction. You may need this for some of your homework problems. Induction as opposed to deduction. So a deductive proof proves usually something directly. An inductive proof kind of takes a different angle. So there's two things you have to prove. First, you have to prove, so this is usually something that's true for, let's say, all positive integers. So first you would have to prove it for n equals 1 or some other small number. It might not be all positive integers, doesn't always make sense to start at 1. So you start at some usually early point, and then you prove that starting at that point and for everything beyond, if it's true for some value of n, then it's true for the next value, n plus 1. And that way, if you have a starting point and you can always move to the next positive integer, then you prove that this thing is true for all positive integers, or almost all. So we'll try an example. We want to prove, we're going to take the sum of the first n perfect squares. And the formula for this is n times n plus 1 times 2n plus 1 over 6. But we don't just want to take this for granted, we want a proof. So let's see. N equals 1, we have 1 squared, and then we have 1 times 1 plus 1 times 2 times 1 plus 1 over 6. That is 1 times 2 times 3 over 6 is 1. Okay. Those are the same. So we have true for n equals 1. Okay. Now, it being true for n needs to imply that it's true for n plus 1, meaning we can suppose our statement is true for n. 1 squared plus 2 squared all the way up to n squared is n times n plus 1 times 2n plus 1 over 6. And now let's see what happens. What is 1 squared plus 2 squared plus n squared? We're going to add the next one, n plus 1 squared. Well, we can substitute that sum with the thing that we know it is. And then we're adding n plus 1 squared. Okay, so maybe let's factor out an n plus 1. Get n times 2n plus 1 over 6 plus n plus 1, which is 6n plus 6 over 6. We can expand and collect maybe n plus 1 times 2n squared plus n plus 6n, so plus 7n plus 6 all over 6. And let's see if we can factor this. This is, let's see, 2n, we need an n, and then we need to add to 7. We have a 2 and a 3, so let's see, we got 2 times 2, 1 times 3, that should be a total of 7. This is kind of factoring by inspection and logic. Okay, so let's rearrange this. This is n plus 1 times n plus 2 is n plus 1 plus 1. And then 2n plus 3 is 2 times n plus 1 plus 1, all over 6. So in fact, this statement is true for n plus 1. Okay, so, and usually you write something fancy sounding like induction follows. So that's how you use mathematical induction. Here's a cautionary note about induction. So here's a false induction proof. We're going to prove that all horses are the same color. How are we going to do that? Okay, let's do the n equals 1 case. One horse is certainly the same color as itself. There's only one color there. And now you have n horses. Suppose n horses are the same color. Okay, now you've got n plus 1 horses, right? So, well, the first n horses are the same color, and the last n horses are the same color, and there's this overlap, which means all n plus 1 horses are the same color. So induction follows, and all horses are the same color. Let's think about what's wrong with this. So induction doesn't actually follow because our base case was n equals 1. To go from 1 to 2, that would mean, okay, our n plus 1 is 2. And when you tried to take the first n, you only took the first horse. And when you tried to take the last n, you only took the second horse. So there is no overlap there. You'll almost never see this in a mathematical example, but you might want to be careful that your inductive step actually does take your base case to the very next case.